All right, so we've talked about our different phases of matter, but now we're going to start talking about changes within the matters, right? Or within matter, changes within the physical state of our matter. So if we think about something that's a liquid at room temperature, why not water, right? If we think about water, we can obviously form solid water by cooling it down, and we can form gaseous water, right, water vapor, by boiling it and heating it up, okay? So if we do that, we can actually make a graph kind of like this. So if we were to start with really extra cold ice, we could then add heat, and we could just constantly add heat at a constant rate, right? We're going to slowly heat it up, and we'll be able to melt our ice, and then we'll heat it up again, and then we're going to boil our water, and then we'll get our gaseous water vapor, okay? And this graph is the characteristic graph as we warm our whatever substance we have. If we were to cool it down, right, it would start high and then go down. But these these horizontal lines are really important, okay? Because at those horizontal lines, what we're doing is we're going from solids to liquids, or we're going from liquid to a gas. And so if we think about our particles, whenever we change phase, right, go from solid to liquid, or go from liquid to gas, we break the intermolecular forces, right? So if we think back to our particles, right, as a solid, those particles are really close together, they're kind of held together, they can't move, right, or they can only vibrate. So to go to a liquid, we have to kind of separate them a little bit and partially break those intermolecular forces. They're still pretty close, they're still touching, but they're not as tightly held as before. Okay, so to get to that liquid, we have to separate those particles a little bit and break those intermolecular forces. And then, to go from that liquid all the way to a gas, we have to further separate the particles, so much so that we totally remove and overcome those intermolecular forces. Okay, so all the way down here, we're going to use this graph a whole lot throughout this unit, right? If we start all the way down at the bottom section, all we have are solids, right? Because we're below the melting point. So we're below the melting point. We maybe are adding heat, but we're still below that melting point. So there is going to be a change in the temperature, right? All we are doing down here is moving those particles faster. So maybe they're vibrating just a little bit, and then we start vibrating them a little bit faster, okay? If we're vibrating them a little bit faster, we are changing the average kinetic energy, so that means we're changing the temperature. But the potential energy does not change, right? While the kinetic energy is changing, the potential energy remains constant. It is still a solid. We still have those intermolecular forces that are holding them together, okay? So the equation that we can use to describe our heat change here is Q equals mc delta T. Q equals MCAT. Q is heat. So if we go down maybe all the way to the bottom here, Q is the heat, right? This is our measure of the energy transferred, right? M is going to be the mass, whatever mass that we have that we're heating up. C is the specific heat, right? The specific heat capacity. So specific heat capacity, right? This is measured, these values are known, they are measured for each of our different substances. It changes for every single substance, whether we have solid water versus liquid water versus gaseous water versus iron, right? It changes for every single substance, but these values have been measured by scientists. So over here, right, in our specific heat column, I'm going to cross that out. I don't actually like that. because we're going to write in a few different values, but we are only going to be talking about water. When we have solid water, right, we are going to do a C value equal to 2.04 joules per gram Kelvin, right? Joules per gram Kelvin or gram Celsius, because, right, if we look at this, our units, when we multiply these together, mass divided by mass, C, joules per gram Kelvin, our change in temperature, right, is going to be maybe degree C or change in Kelvin. That's going to cancel with Kelvin. Our overall unit for heat is going to be joules, okay? So then our delta T, let's make sure that we remember that delta T is equal to T final minus T initial. So in this case, if we're starting at maybe minus 10 degrees and we're going to 0, right, that's our melting point for ice, our final is going to be 0, our initial was maybe minus 10, okay? So we always do, our delta T is going to be T final minus T initial, okay? So then we get to section B here. In section B, we're going from a solid to a liquid. Both states are going to be present at the same time, okay? Both states are going to be present at that same time. So is there going to be a temperature change? No, absolutely not, right? The reason being, all of the energy that we add, as we constantly add energy here, right, we're adding heat. We're constantly adding heat, adding heat, adding heat, but the temperature is not changing. All of that heat is being used to go from a solid to a liquid. We are breaking the intermolecular forces. So we change the potential energy rather than the kinetic energy, okay? The intermolecular forces have to do with potential energy, okay? So the equation that we can use to describe this section is Q equals HF times moles, okay? So HF, we're going to come back down here. HF is the enthalpy of fusion, okay? So it's the energy, the molar energy, the molar heat that it takes to go from a solid over to a liquid, okay? So the enthalpy for fusion, that's what we're going to actually put over here in our last column. Enthalpy of fusion is equal to 6.01 kilojoules per mole, okay? So 6.1 kilojoules, or let's put it as 610 or 6010 joules per mole, okay? This is going to become really important that we make sure that whenever we measure heat, we put it as joules, okay? Because we're going to start adding them together, all right? So then, let's go on to that next section. Our next section here, right, we're going from, right, what would be 0 degrees Celsius up to 100 degrees Celsius. We're getting up to the boiling point of water, right? So we're going from a liquid to a liquid. So we only have liquid present. Do we have a change in temperature? Yes, absolutely. So if we are changing temperature, we are changing the average kinetic energy of our molecules. Okay? So if we are changing the temperature, we can use Q equals mc delta T here. Same equation, but what has changed from before is that our specific heat value is specific to our liquid water now. So I'm going to do specific heat for the solid up here, specific heat for our liquid down here. That's 4.184 joules per gram Kelvin, okay? So whenever we have liquid water, we can use this specific heat value, okay? All right, Now we keep on adding energy. We're adding energy, and now we're at that boiling point. We're adding energy, and we're taking our liquid and changing it to a gas. So again, think about our liquid here. We need to separate those particles. So if we're going to separate those particles, they have to get enough energy to break free of those intermolecular forces that are trying to hold them together. So if they need to get enough energy to break free of those intermolecular forces, we are going to go from a liquid to a gas. We are not going to be changing the temperature. We are only changing the potential energy again, right? The particles have enough energy to stay separated from the other particles and stay, right? They are stronger than the intermolecular forces. So our equation to describe this section then, as we go through that boiling, is going to be similar to our melting point. But our boiling, we're going to use the heat or the enthalpy of vaporization times moles. So the heat of vaporization, the enthalpy of vaporization, is the molar heat that it takes to vaporize our compound. Okay, so if we're talking about water, HV equals 40.7 kilojoules per mole. That is huge, right? So if we wanted to just write that in joules, that would be 4700 joules per mole, right? It takes a lot of energy to completely vaporize our water particles, okay? So then our last section up here, if we collected our gas, our vapor, our water vapor, and we continued to heat it up, right, we would be able to have just gas. And if we're having just gas, we can change the temperature again, right? We don't need to change the potential energy. We now need to change the kinetic energy. We need to heat up our particles and change that average kinetic energy. So again, if we are changing the kinetic energy, right, all of our diagonals on our graph, we can use Q equals MCAT. But the C value here, again, changed. So we're going to do C value for gas is equal to 1.996 joules per gram Kelvin. Okay, so these values again are specific to water, right? So our specific heat of ice, the heat of fusion for ice to water, our specific heat of water, the heat of vaporization, the enthalpy of vaporization to go from liquid water to gaseous water, and then our specific heat of gaseous water, okay? So what we want to be able to do then is to use these equations to describe as we change things, okay? So that is what we will be doing and working on the worksheets.